Okay, so I started recording. Caitlin, you weren't here in person, right? That was
correct.
And so, you know, for you or others who end up missing it, you know, as we mentioned, all the recordings will be posted online eventually. I mean, maybe not immediately after class, but within 48 hours. So, you know, if you go to the GitHub, you should be able to get access to this folder where we'll be putting each lecture and lab recording. Please tell me if you can't access that. We also, I learned previously to start putting up simple examples of different TMB features in this TMB examples directory on the GitHub. So in this case, the only thing I've put up is this map argument, and we'll start talking about the map argument, I think starting in week 3, although I forget, maybe week 4. And the long story short, the map argument is how you can either turn off parameters. So if you build a model with extra parameters, you can turn them off so that they stay at the starting value. Or you can mirror parameters. You can make a bunch of parameters use the same value. And again, that is demonstrated in R and CPP code there. And today, obviously, we'll go through this lab 1 material. I'm trying to think. There was some other piece of logistics that I was going to have somebody remind me. Anybody remember? We were just talking about it this morning. It doesn't matter. If it matters, it'll come up again. Okay, so yesterday, well, Tuesday, we tried to do a quick overview of why we, how we estimate things, why maximum likelihood estimation is a good option. Can anybody remind me kind of what my 3 listed reasons were for why maximum likelihood is a good estimation kind of paradigm?
2, more consistency.
Yeah, exactly. So
Consistency, you're correctly specifying your model, and if you're incorrectly specifying your model.
Yeah, exactly. So you get the consistency with a true model, which is nice in simulation testing, is a way to make sure that you coded your model right. Basically, if you can't confirm that it's consistent when your estimation model matches your operating model, you probably have a bug. What were the other things we talked about?
Transformation parameters.
Well, there's the transformation. That wasn't the one that I'd listed, but it's a good property that you can reparameterize your parameters and often end up with the same maximum likelihood. End up with when you estimate the parameters, you will end up with the same model, meaning the same predicted values for all your data. Other stuff?
The normality, so as your sample size increases, it should converge around some sort.
Yeah, exactly. So there's an asymptotic normality of the estimate around the true value or the optimal value, and the optimal value should remind you that the other one that I stressed was that maximum likelihood is guaranteed asymptotically. As you increase sample size, the parameter estimates are guaranteed to converge on an optimal estimator. That optimal estimator is the one that minimizes the Kullback-Leibler divergence between your model predictions for each datum and, in the data generating process. So those are some benefits. Today we're going to go through generalized linear models. So, take what we were talking about and extend it to other distributions. So. We'll do this again because next week we'll get into generalized linear mixed models, which is the next extension, and from there we transition into spatial conformal models. So generalized linear models have 3 parts. You have to specify a distribution for your response, your data. You have to specify a linear predictor, and then you have to specify a link function that transforms your linear predictor into the parameters of that distribution. So, for example, a lot of spatiotemporal models start with what's called a log Gaussian-Cox process. And a log Gaussian-Cox process is just a fancy way of saying you've got a Poisson distribution for your response, and you've got a log-linked linear predictor for your counts. We'll talk more about that in a bit.
What do you call it? Gaussian?
A log Gaussian-Cox process, or sometimes people call it like a homogeneous or inhomogeneous. I mean, you know this vocabulary maybe better than I do, John. Tell me if I'm.
So the idea is you have a spatial process that describes the intensity of a point process. So point process, you just get what you're interested in is the locations of animals, for example. So you would describe the intensity of those with some sort of underlying Gaussian process, which we'll get into later in the course, but a spatial description of that, which may have the same properties everywhere or not.
So we can talk later about why that sort of definition, where the random variable is the location of different events, is identical to a Poisson generalized linear mixed model later. We don't really have the vocabulary to get into the details yet. But. Yeah, so that a few examples of discrete value distribution. So any kind of data where you're counting some things. The only ones that I think I have ever, well, these are all univariate ones. So you could have, and I'm trying to be better about my notation where on the left-hand side you've got a random variable that's a capital letter, not italic. That random variable is to the left of a tilde, which means that there's some stochastic process, there's some distribution where the right-hand side is a distribution function. Probability, in this case, a probability mass function. So, the common ones are a Bernoulli, and we'll talk more about where you would ever use these. So there's a Bernoulli where the input is a probability that can range from 0 to 1. So it's like a coin flip. The binomial, which is a series of coin flips. The Poisson, which is, we'll talk more about in a bit. The negative binomial, which is a generalization of the Poisson, and the Conway-Maxwell Poisson, which is a generalization of Poisson as well. So the key to this is that there's sort of these two where the input is a probability that ranges from 0 to 1. And then these three, the parameterizations I'm using all have an intensity lambda that is the expected value of that process, and then possibly some other variance parameters. I'll come back to how we derive these. And then common distributions for continuous data. We might have a normal, a log normal, a gamma, a beta. So these are sort of the toolbox of different distributions that you might think that your data could follow. And then I think there's only really 3 univariate link functions that I ever use, or that we will probably have to use in this class. Is this vocabulary, have people studied, how about raise your hand if you haven't studied generalized linear models in some other class? Okay. So we're kind of breezing through it, but the point, again, every generalized linear model has 3 things. It has the link function, it has a linear predictor, and it has a distribution. And so these link functions, this is a linear predictor where you've got a vector of coefficients beta that's multiplied, that the expectation for each of these, or some input for each of these, is the product of this vector of parameters beta times a row of this design matrix. And in a simple identity link function, the intensity for a Poisson that has input lambda could just be this linear predictor, and it's called a linear predictor because it should look like kind of like a linear model. And so if you have an identity link function, this product can range all the way from -infinity to infinity. And so the domain, lambda on the left-hand side can range anywhere from -50 to infinity. The log link, by contrast, is nice because the output lambdas ranges from 0 to infinity, even though this product ranges from -50 to infinity. And why does that matter? Why would we use a log link?
Some things can't be negative.
Yeah, so there's a lot of distributions where the input is restricted to be a positive number. So let's see, what would be an example of an ecological process where you don't have any negative numbers?
Cash.
Capture, exactly. Yeah, so we never have negative densities of fish. So the expected number that you're going to see in a given sampling will always be 0 or greater. And then the logit link, there's this tradition that we call the link the function if you transform it on the left-hand side. And so the inverse link is how you transform the linear predictor. And the inverse of a logit is just a logistic function. And so this logistic function guarantees that lambda is between 0 and 1, even though the linear predictor, again, can be anywhere from -infinity to infinity. So what are some examples of something that we would want to bound from 0 to 1?
Any sort of rate,
What's that?
any sort of rate in the population, like prevalence of the disease. Or
Yeah, right, exactly. So proportions, like proportion male or female, proportion sick, not sick. Did you say something?
Present substance?
Yeah, presence absence. Well, yeah, exactly. So presence absence usually is either 0 or 1, but the kind of expectation, the expected probability of it being present or absent is, could be anywhere from 0 to 1. So like any probability, like a coin flip model, a Bernoulli or binomial model, the probability has to be bounded from 0 to 1. Okay, well, so we started going through this. So we've already listed here, I think that was 8 different distributions. And those are all univariate distributions. So if you get into complicated models, you get multivariate distributions like a multinomial or a Dirichlet or a multivariate normal. And we can talk about those later. So I guess really choice 0 is it univariate? Is there just a single response, or is it multivariate? Is there multiple responses? Here it's assuming they're all univariate. And then from that, you've got this, you look at your data, is it continuous? If it's continuous, you have to use a continuous distribution. If it's discrete, technically you can use a continuous distribution or a discrete distribution, but we'll focus on discrete ones. And then the choice 2, what's the range of possible values of your data? So if your data can only go from 0 to 3, 0, could include 0, 1, 2, or 3, then that can't be a Poisson distribution because a Poisson could go greater than 3. So if people are not familiar with these, you can go back and look at the notes later to refresh what the domain is, the range of each of these. And then finally, the third choice is how flexible do you want it. So like if you've got a count process, well, we can come back to that. Okay, so I'll argue that the three null models that we ever, if you don't know how to model your data, there's probably 3 places to start. So briefly, sort of when did you use a binomial model?
Doing anything with probabilities.
So yeah, so it's anything where you're modeling an event where each event has a certain probability you want to model. So if, like what's ecologically wide, where might that come up?
Death or survival.
Yeah, so a lot of like marker capture experiments end up having a certain probability of dying or being captured every year, and that's a Bernoulli, that's a binomial in which you have a single coin flip. They also come up a lot in like site occupancy models or site abundance models. So if you've got a model where you think there's 10 salmon, between 2 different you've got a stream and you put up nets on one side and the other side so that they're demographically closed, and then you start doing electrofishing or gill netting or something, then each time you do that, you could get between 0 and 10 individuals, because that's how many possible individuals there are. Okay, Poisson distribution, where use that.
Sometimes when there's patchy distributions and things,
Yeah, so,
or
Yeah.
random.
yeah, right, exactly. Let's come back to that in a second. We'll talk more about this, and then the normal distribution, where do we,
There all the time.
all the time, exactly, yeah. Like heights, the distribution of heights in a classroom is, well, it's 2 normals typically, because there's sort of an average height for males and an average height for females. So that's technically a mixture distribution where you have some combination of 2 different distributions in your population. Okay, so how do these come up? So technically, the Bernoulli, where this, I should have made these non-italic. I'm probably going to be lazy about that, whether I need to use italic or non-italic for but so if you've gotten a binary event like a coin flip, that coin flip has, if it's a fair coin, it has a 50-50 probability of being heads or tails. Then if you do, so if you have a Bernoulli distribution, the left-hand side is a random variable that can take the value of 0 or 1 or heads or tails or whatever, male and female. It's just a thing with 2 categories where there's a certain probability of getting heads versus tails. And if you do that experiment several times and count up the number of heads, then that's a binomial. So that's what that's saying. So Bernoulli is just a binomial with a sample size of 1. And the characteristics that should be kind of obvious are, if you've got a 50-50 chance of a heads or a tails and you do 10, coin flips, what's the expectation? What's the most likely value for the number of heads? Yeah, 5. And then the variance, this variance formula suggests that as, I should have put on the plot, I suppose, but it says that the variance of the number is greatest, at the intermediate value. So, if you have an unfair coin where there's a 100% chance of it coming up heads because somebody's rigged it somehow, then there's 0 variance. And similarly, if there's a 0% chance of it coming up heads, there's 0 variance, and the variance is maximized with a fair coin. Okay, so let's work through the Poisson again. So, let's see. It comes up in physics a lot. So, like, if you have like a radioactive material, so if you've got a lump of uranium, and you've got a Geiger counter, the number of what do they call it, where like one molecule becomes a simpler molecule. The number of reactions per second is some property of the material, but the number of times it happens per second is a Poisson distribution. I don't know, where are the other case, where do people see a Poisson? Let's start with that. People use.
Like when there's like, sort of like you said, like an event that like on average occurs a certain number of times, but like it can vary, between time periods.
Yeah.
So like number of people passing through a gate or something.
Yeah, right, okay, yeah, exactly. People passing through a gate, it comes up a lot in like internet engineering, where the number of people that will hit a website or, what are they called? Those backbones, DNS. Like if you study how much server space you need to understand a Poisson distribution.
And the key is that they're independent.
Yeah, exactly. So these are all examples, like the physics example is nice because those molecules of uranium that are breaking down are not communicating with one another. They each just have some independent probability of decomposing, of changing from uranium to whatever the next thing is that they become when they become less unstable. So yeah, so if you have a lot of independent events, each with a low probability, the way I like to think about it is just this sort of, deriving it from a binomial distribution. So if you take any binomial process, like a coin flip process, and you do it such that the product of these is really big and the probability of each individual is really small, then you end up with a Poisson. And you can see that where if this p becomes really small, then this goes to 1. And in that case, this term drops out. And so binomial with a really small p just has an expected value n times p and a variance of n times p. And that's the same moments as the expectation of a variance of the Poisson distribution. So, in this physics example, if we have 100 million molecules of uranium, and each one has a probability of breaking down to what the next thing is in that chain, the reaction chain of uranium as it decays. Each of those has a really low probability of decaying per second. And so technically it's a binomial distribution, but we can approximate it as a Poisson because these properties are met. Okay, and then a normal distribution. So why does a normal come up all the time?
Central limit theorem.
Central limit theorem. Yeah. So if you have any density function, it could be it could be a probability mass function, or it could be a probability density function. So it could be counts, or it could be measurements. And you take the sum of different outcomes. Sorry, so this should be capital B down here. You take the sum of a bunch of these independent ones, and that sum will converge on a normal as you take the sum across more stuff. So being ecologists, if we randomly select men and take their height, why does that end up being a normally distributed, follow a normal distribution?
You're less likely to be of an extremely tall or extremely short. Most people are most likely to be somewhere in a middle range.
Totally.
And
Yeah.
so that creates that bell-shaped curve.
Yeah. But why genetically is that happening?
It's like the sum of a bunch of genetic processes or something.
Yeah, right. So height's one of these things that, we've got, 10,000 genes, or, some combination of genes and methylation and epigenetics and all sorts of crazy shit. And, we've got 10,000 of those random draws that contribute to our height. And so by the central limit theorem, we're all guaranteed to kind of be, somewhere in the middle. Okay, so, and as the number of events gets large, the expectation for the sum across them is just the number that you did times the expectation of each individual process. And the variance is just the number squared times the variance of each individual process. And so this is sort of a property of algebra with random variables that we're not going to get into further. Okay, so and then the review of maximum likelihood estimation is that we can define a probability for each of our data given a set of parameters and given a model. And if we invert that, if we define the likelihood of the parameters given the data, we can maximize that likelihood with respect to the parameters, and we get a good estimator. That's what the asymptotic theory of maximum likelihood suggests. And what we didn't really talk about is this argmax step. How do you maximize that likelihood? So here's a few slides about sort of nonlinear maximization or minimization for people that are not used to doing this. And I should say that I do understand that this is like a little bit dry. I still think it'll get more interesting as we go, but we all need to go through these set of basics together. Okay, so technically I'm going to minimize a function called a Rosenbrock banana function. So this function, like if we start out here, this is a contour plot where the minimum is at this red circle, and the minimum is at 0. And if you start way out here, the contour lines are these black lines. This is the log likelihood of like 100 million out here, and the maximum gradient is going this way. And so if you start out here, the smartest path to follow is going down the gradient. Technically maybe it's up here. But then once you hit this valley, you have to make this sharp left turn and radically change what gradient you're interested in. And then you follow this gradient down here, and it's called a banana function because this valley is banana shaped. So if you start here, you've got this sort of tough decision of which way you go, and then you have to follow the banana. And that's why this was sort of like a test of optimizers back in the day. So, well, I don't know. What minimizers have people used, or have people ever paid attention to what minimizers you're using? Yeah, so, okay, well, how about this? So it's already kind of given away here, but we talked about Kepler being the person who started doing something like least squares, where they, would take measurements of a wobble of a planet and take the average of that and say that's a good estimator to deal with the wobble of his hand when he was looking through a telescope. So who is the first person to then start actually doing formal maximization or minimization? Newton. Yeah, so Newton, one of the two developers of calculus, came up with this method where you could, maximize or minimize a function by going the direction of the gradient, where the distance you go depends on a second derivative. And so quasi-Newton methods refer to methods where the optimizer tries to figure out what the gradient is locally by doing a bunch of finite difference calculations, and then it goes in the direction of that numerical derivative. So if you start out here and you use a quasi-Newton, it follows the kind of gradient, and then it just gets kind of stuck here for a long time. And any guesses what it's doing there, why it's having trouble once it gets there?
It's not taking large enough steps.
Yeah, well, it's not taking large enough steps. Any guesses why?
Gradients will low.
Yeah, right. So here, this gradient is incredibly steep, and then it hits the valley, and this valley has a gradient that's like 1/1000th or 1/1,000,000th of the gradient that it was following. So it follows the gradient, and then it hits the valley, and then it just gets really confused about which way to go along that valley, and it has to basically shrink the distance that it's using for this finite difference calculations. Has anybody used a Nelder-Mead? And what you know what a Nelder-Mead is doing?
No.
Okay. So a Nelder-Mead is like a little amoeba where in 2 dimensions it's got a triangle, and it's just randomly choosing one of the vertices of that triangle to flip over, and if it moves in the right direction, it just uses that little amoeba leg to expand and contract until it hits, stops improving, and then it flips another vertex in the triangle. So if you have a 1,000-dimensional model, it has to be tracking 1,001 amoeba legs and keep flipping each of those around.
But it doesn't require gradients.
But it doesn't use gradients, the main way. So if we click play on this one, you can kind of see that it's doing these like funny long steps, but it gets there a lot faster than the quasi-Newton. It's not tracking gradients, and so it doesn't get as confused about that change in scale. Let's see, and then if we go to the next slide, the punchline is we'll be using TMB with using Nelder-Mead. Where it just goes a lot faster. So like that one compared with this one, this Nelder-Mead is taking about 4 or 5 times longer to get the same distance. And that's because basically every frame is kind of getting stuck because it's doing a bunch of evaluations to kind of do these amoeba legs, move different vertices in the triangle, and it keeps trying different vertices to flip and finding that those aren't useful. And so it's spending all this time trying to figure out which leg to move, whereas the Nelder-Mead using TMB just knows the gradient and it knows which way to try to move. So for the remainder of the class, we'll be using a Nelder-Mead algorithm using Template Model Builder that uses gradient information. And this, that's as far as I'm going to go into nonlinear minimization. So we'll basically take as a black box that we can use TMB to get we can specify a model and write it down in a CPP file, and TMB gives us the gradient of that function with respect to any parameter. And we use that in a Nelder-Mead algorithm to figure out what's the maximum or minimum. And then how do we check convergence? Well, I'm going to recommend that we always check to make sure that every gradient, we talked about this yesterday, a maximum or minimum has a gradient of 0 with respect to every parameter. But as Grant pointed out, you don't actually get the exact same estimate because the nonlinear minimizer will give up sometime when it's close to 0. So for convergence, I want to make sure that every parameter has a gradient of less than 1/10,000. And that's sort of arbitrary, but that's sort of a basic rule that I'll have for the class. And then you need to check the Hessian matrix to make sure it's positive definite if you're doing it, minimizing a negative log likelihood. And we'll see how to do that later. Okay, so any questions about this?
So for TMB, knowing the gradient, that's why it's so much faster. Does it calculate it at like every feasible point on the probability surface? How does that?
You mean like on what probability surface?
So how does the optimization algorithm in TMB like sort of implicitly know the gradient or like prior functions that we're trying to minimize it didn't?
Yeah, so and I'm not going to go into automatic differentiation too much, but why don't we come back to that in a minute? We'll get to that by the end of this. Why don't we look at the CPP code and we can talk about it once we're looking at that. Okay, so we're coming back to this canary rockfish example, and the homework that is, that I'm assigning today is due at the beginning of class, at the beginning of the lecture next Thursday. That homework is going to be doing something similar using another data set for pollock in the Eastern Bering Sea, which is the fish that if you've ever had a McDonald's fish sandwich, that's pollock you were eating. So we should all feel a deep affinity for pollock. So again, let's pretend we want to figure out what's the average catch rate for canary rockfish in this survey that we're not really talking about in any detail. And if we want to just take the average, we can specify that this design matrix X is a single column matrix with a row for every observation, such that if you take X times beta, beta is just the intercept parameter. That's the linear predictor. And okay, so the issue with this data set is that we might want to do it with we might want to fit it with a generalized linear model. So let's just open it up. So the top of this code is some stuff where top of this code is code to remake those animations that we looked at. Have to read your overhead, you guys. Okay, so can people see these two screens okay? Should I zoom in a little more? Is that enough? Sorry that it's not.
Maybe we can dim one of the lights.
Yeah, okay.
That would help much.
These two?
Other side. Yeah.
Okay, so, you know, you guys will have to change the set working directory. So the set working directory is telling TNV where to look for, you know, telling R where to look for files. And of course, I downloaded it on my machine where I have stuff loaded into something called Project Git. And you'll have to change that based on the location of your files. And then I loaded TNV. Next, I'll do this DevTools install GitHub. And actually, maybe I'll change this code. So, as I said yesterday, this first install GitHub is installing a package that I've put together that it just ships with some data. So the data sets we'll be looking at are installed from Geostatistical Delta Glim on GitHub. And then this install GitHub TMV helper is a package that I put together that kind of eases the optimization process for Template Model Builder models, and we'll start using that today. So anyway, so it's taking a while to download this stuff. But, so we'll load this data, West Coast groundfish bottom trawl survey canary example. And we'll extract CPUE, which is a histogram that looks like this, where 7,000 samples have less than 500 kilograms observed, and then I guess there's some single sample that gets up to like 6,000. And let's see, mean CPUE equals 0. So 92% of samples are zeros, where we did a sample and we didn't see any canary rockfish, and only about 7% of samples actually observed any. But the 7% that did observe some had a mean of 39 kilograms of canary rockfish, and the maximum observed was almost 5,000 kilograms of canary rockfish. So this is a really typical, there's some community colleges call this a dustbin distribution, where if you look at a bunch of different species all at the same time, most samples are 0, 0, 0, 0. They're, where like dust gets in the corner. And then occasionally you get some like dust that kind of gets along one edge of it, where you get a lot of a couple species and 0 of most of the other ones. Okay, so the problem is that so what would be the distribution we want to use for these data? I mean, they have zeros, so we can't use a log normal distribution or a gamma. I mean, what distributions could we use for this?
Do you want negative binomial?
So we can't use a negative binomial because a lot of them are not whole numbers. It's kind of a trick question. I'm sorry, I'm just trying to get people thinking.
Densities, not counts.
Exactly, yeah. So it's biomass sampled, and it could be any real number. It's not an integer number. So it can't be a Poisson or a negative binomial or a Bernoulli or a binomial.
The log normal?
It can't be a log normal because it has some zeros. Like if you take the log of CPUE, you get a bunch of negative affinities. And so, I mean, so like yesterday or Tuesday, we fit a normal distribution of these data. So that's allowable, but it's kind of, and that's equivalent to doing least squares, as we talked about and showed. But that sort of sucks because a normal distribution has a bunch of mass below zero, whereas this is bounded at zero. So it's not really clear that there's any distribution that works great for this. And so instead, us fisheries people, well, anybody who's used to doing biomass sampling data, so fish people, or there's insect traps. Well, why don't in what other cases might you end up sampling biomass?
Do you count humans as, like, number of humans times the average weight of humans? That'd be super fun.
Yeah, that would be pretty awesome. I think that there could be like blood assays where this might come up. I'm not sure though.
I do like metabolic risk factor work, and very rarely I'll work in like population space, blood pressure, like person millimeters of mercury,
Yeah.
but it's never like practically reported.
Yeah. I mean, my feeling is most public health stuff is counts, but yeah, I'm sure there's some medical applications where people do. Whatever, bacterial loads or whatever in the blood. As ecologists, are there other cases? I mean, I mentioned fish weighing. I said insect traps, light traps, like in the agricultural fields where people at night put up a light and then they count the number and basically they use a net to count the number of insects near it. There's a couple other cases, ecologists, where we get this. Another big one is leaf traps. So like if you want to count like the output of, the reproductive output of a plant, you might put a bunch of pollen traps near it, or count the number of chestnuts that fall in or the number of leaves as a measure of photosynthetic output. Anyway, so there's a lot of cases where this comes up, although it's sort of, fisheries probably comes up more in fish than other fields. And as a reminder, I mean, a lot of these things we're doing just come back to the three kind of laws of probability, or so the axiom of conditional probability is that if we've got two events, x and y, we can always factor it into the marginal probability of one and times the conditional probability of the other given the first. And so in this case, we're wondering, what's the probability that a given catch is 0 or non-zero? And then what's the probability distribution for the catch given that it's non-zero? And that's, and so we end up with a delta model is defined as a probability that some catch equals what we observe is the product of these two different things, and we'll end up defining a generalized linear mixed model for each component of this eventually. So that's what we call a delta model, or it's sometimes called a Bertle model. And so the simple kind of delta model we'll be looking at today is that the probability that a catch is equal to 0 is equal to a parameter lambda 1, and then the probability that it's the distribution for non-zeros is equal to the probability that it's not 0 times the distribution for this, times a log normal or a gamma or some distribution for the non-zero counts, non-zero observations. So what's the minimum number of parameters that this delta model would have? Yeah, 3. So there's this, I'm sorry, this is a theta, what was I saying, lambda? There's a theta 1, which is the probability at 0. There's a theta 2, which is the variance of this log normal. And then there has to be at least one parameter in this beta, this vector beta, where if it's a single parameter, it means it's just the intercept. So this is the probability of the data, and in general we want to use the log likelihood, or flip around the log probability. And so if we take the log of the left, we want to take the log of the right-hand side. And so the log likelihood is this, where the probability is, the log probability that 0 is just equal to the log of data 1, and the log probability if it's not 0, the log of a product is equal to the sum of the two logs. So we get this log plus this log. Anybody want to walk through that more slowly? So the point is that we'll end up using this log likelihood as the distribution for the data in the delta model that we'll be using. Okay, so I'll go through the TMB code in detail now. So the length of CPUE is a vector with length 7,608 observations. X is a matrix with one column with that same number of rows. And the delta model code looks like this. So do people, so when I taught this class before, I had about an hour and 20 minutes for the Thursday, and now we have a lot longer of time. I don't know, why don't we take a show of hands? Like who here would think it's more helpful to kind of work in groups for a little while, looking at the code individually versus going through the code as a group and then trying to modify it in breakout groups? So who would like to work in groups first? Okay, and who would like to work through it as a group, as a class, and then break into groups later? Okay, who has no preference? Yeah, so it was like 2 and 2, a good even. So based on the vote, we would just like have a deadlock. And
Well, the remote people prefer like going to SF.
Okay.
There's strong online preference.
Yeah. Okay, so we'll spend maybe 10 minutes going through this code, and then we can break into groups a little bit. So the first new piece of code here is that I'm defining a function, and this is sort of C++ syntax. So on line 2 of the file delta model version 1.cpp, the first line is this include tmb.hpp, and again, I don't really know C++ enough to know what that does exactly, except that I need it for me not to have a compile error. And looking at the name of the file, it makes sense that it's just some shit related to TMB. Then I define this d log normal distribution to look, well, I call it d log normal, but it's basically the same syntax as the dl norm function in R. And I can't remember if TMB now maybe has a function called dl norm, but when I started using TMB, it didn't. So I got used to building my own functions, and I think it's a useful thing to get used to doing. So that's why I'm demonstrating it here. So we talked really briefly about how, okay, here, why don't we talk about AD for a second here? So when we, on Tuesday, we built a program in R that took the mean using a d-norm statement for the log likelihood from a normal distribution. And we ran it, and why was it worse than TMB? What were the problems we identified with it and compared with the TMB code we got to?
Well, its cutoff for optimization was like lower.
Yeah, exactly. So it got to the third decimal place relative to what we knew to be the exact way of doing it, which is just the average of the data, whereas TMB kind of optimized it more fully. It was also a little slower, although I didn't really show that. So that R implementation, it was vectorized, so it wasn't slower because it was doing a loop. It's a little slower in R because it's an interpreted language instead of compiled language. But the big benefit of doing things in TMB is that it's overloaded to do automatic differentiation. And the 2-minute explanation of that is that this is all using templates. And a template is a thing in C++ where you can overload the meaning of operators. So Casper Christensen and Brad Bell and the people who developed TMB defined this new type. It's not a double and it's not an integer that you'd use in C++ typically. Instead, it's a type called capital T type. And that capital T type is an object that's tracking the value and also the derivatives of it automatically. And all of the algebra, every function we're using in here, like dividing and plus and exponentiating, all of those things that we're writing out are overloaded to work on both the value and the derivatives. And so it looks like normal code, but in this kind of brilliant way, it's just using a normal code, but it's all overloaded to simultaneously be tracking the value, the first derivative, the second derivative, the third derivative, all of it automatically, and which is why it's called automatic. Well, that's one reason. And automatic differentiation, meaning that it's automatically tracking these derivatives. So you get all of these derivatives automatically as long as you write your code in C++ and you put this include tmb.hpp at the top, and as long as you define all of your values as type. And so if you compare this with normal C++ code, it looks identical, except you've got this annoying vector caret type, which is saying, for instance, that linpred I is a vector with where the elements of that vector are of type. So I don't know C++, I don't ever code in it except in TMB, and I think by example you can pick up basically everything you need to know about C++. But that's why you see this capital T type over and over again. Okay, so template. Yeah, so, and yeah, Dan Ovando is saying that there's a series of packages that are in C++ that are templated, and any templated package you can use with TMB, and it just automatically works and does derivatives. But not all packages in C++ are templated. So there's a set of packages that we'll use that we'll introduce slowly throughout the class. But in general, you don't want to just randomly use new stuff in C. The stuff, if you use C++, you don't want to use the same normal packages. You want to be careful about what other packages you might load. Okay, so this function, dlnorm, is saying, again, I don't know what template class type means, but you put it at the top of any function. And then I always have these unary functions where the return is a scalar of type. And then the name of the function is dlnorm, and then it has a series of inputs, one of which is type x, one's type vlog, one's type sdlog, and the final one is whether you want to give it the output to be log normal or not. And it's set up to have the same things as the R function. So x, mean log, sdlog, and log equals false by default. So and then internally it calculates something of type called the log result. And that log result is just equal to a normal distribution minus the log of x. And this is technically the Jacobian of the transformation, and I don't really want to get into it too much. But this is the probability density function for a log normal. And then it uses this sort of terse way of saying if give log equals true, then you return the log result. Otherwise, you return the result not as log. So that's what. So this does any questions about this sort of terse function? You can also, I mean, a person could just confirm if they wanted that log result is equal to, or the result is equal to that top thing. Actually, wait, no, that's just a normal distribution, not a log normal. Okay, so that's the way you can build a new function. And then the main function of this is uses the same template class type, and then it has this line that, again, I don't really understand what it means, but it's at the top of every main function that you use in Template Model Builder. And then it defines the input data, the parameters, does some calculations, and returns the joint negative log likelihood at the bottom. And so I compiled it already, I do this in R, I compiled it, I do this 9 load statement. I make a tagged list of parameters and data. So the names of this tagged list for parameters and data needs to match the names that it's expecting in the model. So params has b comma j and theta comma or underscore z, which is my way of saying that this is b is a vector that's subscripted by something called j. This is just my programming style, but you'll see it over and over, so I won't explain it. Theta is a vector that's subscripted by something called z, something else called z. And then data is lowercase y for a vector subscripted by I, or x, which is a matrix, so it's uppercase subscripted by I and j. And so just looking at this, we can already see that this kind of matches the same vocabulary, notation we're using in the equations, where I is the number of data, xij is a matrix with as many rows as the data and columns as j, and beta j is the number of linear, the parameters of that linear perimeter. Okay, so then we do this logit transform. Well, this is a logistic transform, or an inverse logit transform of data. The first element, well, I'll say one more thing about the input. So data vector is a way of saying that it's a vector. The input is a vector. And data matrix is its way of saying the input is a matrix xij. And that matches the type on the R side. So is matrix data xij. Yes, it is. Is it a vector? No, it's not. So the type on the R side matches the notation of the input for the data. And the same thing is true of params. Is vector params b underscore j true. So one way you could break this model, and it would give a compile error, is if you replace parameter vector with parameter scalar, in which case it would think that b underscore j is just a single thing, instead a scalar instead of a vector. So I can show you that breaks the compiler.
So those data vector, data matrix names, those are like TMB.
Yeah, so technically in C++ those are called macros, and that doesn't really matter. Yeah, it's some code that Casper wrote into TMB. It's a way of inputting stuff. And I don't, you can look that up on, I can show you the DocStudent documentation for TMB, and it's a little bit sparse. And so again, I think the best way to learn that is by example. There's something called data scalar, data vector, and data matrix. And those are really the only things you're ever going to have to use.
Does it not care about row versus column vector? In span, that's the thing it's really annoying.
Yeah, exactly. As long as it's a I don't know what it would do. R doesn't really doesn't distinguish those. So, it's set up to be very similar to R.
Okay.
So if you put in a matrix with a single row and a bunch of columns, and it shows that way in R, then it needs to be a matrix on it.
And that's functionally a row vector.
Yeah, and that's functionally a row vector. But you know, like in R, people don't usually, I mean, if you extract a row of a matrix in R, it automatically reduces it to a vector by default. And that's sort of the same way that TMB is thinking about it.
Right.
Yeah. So like, parameter, oh yeah, I'm sorry. So this is me demonstrating, I forget the code. If you have a data scalar, you need to call it data scalar, but if you have a parameter that's a scalar, it's just called a parameter. So that's, I guess, one exception. And again, these aren't that interesting, and they're also, I mean, there's maybe like 3 examples that you have to remember, so I think it's easier to learn by example, typically. Well, I'm not gonna. Okay, so I'm gonna recompile it after having eliminated my demonstration of a bug. Okay, so we showed that the params and data match what it's expecting on the C++ side. And then we do this make AD fun again, where you give it the data and the parameters, and in this case, I'm telling it the DLL name is this, which is just kind of redundant, and it's just a reminder about what I'm loading. So as we saw before, we've got params bj equals 0 as the starting value, and params theta params $theta has 2 values. So this is the simplest delta model. It has 3 parameters. They're all starting at 0. And if TMB obviously understood that because obj_par has the same names and it has 3 values, they're all at the same value that we set the starting value of. The next step is to optimize it. So for now, I'll just show you that the obj_fun works. It returns the negative log likelihood. The gradient returns a vector of length 3, which is the gradient of that log likelihood with respect to every parameter. And it's giving that gradient again because it's this overloaded usage of type that allows it to calculate the gradients in this efficient way. We can pass it this stuff, and here we see that the gradient declines as it does this call over and over. We then can check diagnostics. So I'm adding a slot called opt diagnostics. It's a data frame. And so this has the name of each parameter, the estimate, and the final gradient. Each of those final gradients is within 0.0001 or 0.0001. We can look at the estimated parameters, which we already did, and then we can run the SD report, which tells it to do the delta method on the model. I'll show here that, well, let's see, maybe I'll just do this, AD report, 0 prob. So at the bottom of these files, there's some code report, which is in caps lock, and again, that's a TMB specific macro. Anything that's in caps lock is sort of TMB code. It's not typical C++ code. And so we can see that report, well, there's the typical outputs are report or AD report. So we can run a function called report equals obj report. Well, why don't we look at what this is? So if we do args, it's a function where the parameter value is the last par, which is kind of confusing. But last par matches the estimates. And so the short summary is that TMB, while it's doing the optimization, it's also keeping track of what's the best value it found. But it doesn't do it exactly the same way that the optimizer does it. So if by default you run obj report, it's equivalent to saying that par equals obj and last par. And then it spits out, sorry, this is kind of confusing, but the names in this report, it's a tagged list that has stuff corresponding to each thing that we reported out with this macro. So the report function is your way of exporting all of these intermediate quantities that you might want to do. And you can figure out what those intermediate quantities are by putting in other values. So say we want to figure out, oh, what happens if we change one of the values? You know, what happens with the starting values, say? So what are the outputs for that report if we use the starting values? Well, in that case, log SD equals 1. Because the opt_par log SD is just this value exponentiated. So report is your way that you can extract any kind of intermediate quantity that you want, and that's nice because you can debug with that, or you can get diagnostics or anything. Did you have a question?
Yes, so sorry, what's the difference again between obj and last par and then the optimized object par, and which one should be used if we're trying to get like the final?
Yeah, I would use the opt_par. And so really, like for careful programming, anytime you run report, and I probably didn't do this. Down here I did the report. I probably should say par equals opt_par. Okay, so that's what the report does. Here, I'm just going to unload this, and I'll explain what I'm doing in a second. So I'm unloading the model, and then I'm going to recompile it right now. And I'm recompiling it because I just added this new line, AD report, and I added that because I wanted to show what AD report would do.
Yeah, what's the difference between AD report and report?
Yeah, so report you access using that $report function, and you can do that to get any derived quantity or intermediate quantity or whatever. AD report is your way of telling it that you want to calculate the standard deviation for something. So AD report is triggered when you do this SD report command. So I recompiled it just now. I'm going to re-optimize it. And that worked. And it looks like the same object, but you can do SD, summary SD, and suddenly we see that we've got an estimate. We've got the same estimates for B, J, and these two thetas, but now we've got another row called zeroprob. And zeroprob is showing up because I told AD report zeroprob, and zeroprob is the logistic transformation of that first theta. So if we do, I was forgetting R, how to do this stuff. Yeah, so plogis is a logistic transform. If we do a logistic transform of 2.54, we get 9.26, which is that zeroprob calculation. The benefit of doing this is that, conceptually, I'm not going to talk about it too much. It conceptually makes sense that if we get the standard error for this theta, we could use that value and the standard error to calculate the standard error of a transform value. And the precise way of doing that in maximum likelihood is called the delta method. And it's doing the delta method internally to calculate that standard error for a derived quantity. So that's the value of AD report, is you can use it to calculate the standard error of any derived quantity you want. So like an R, that might have been harder to do. You'd have to either know the delta method, program it yourself, or you'd have to dig up some package to do it. Whereas in TMB, it's really easy to start getting standard errors on stuff, derived quantities. Okay, so, and then here, I'll finish getting through this example and then we can break into groups a bit. So, as I want people to get in the habit, you can check convergence by confirming that opt or all. Yeah, so the opt diagnostics final gradient is this thing that I made that has the final gradient. If you take the absolute value of that, they're all less than 0.001. So this statement's true, meaning that it had a good convergence. And then the positive definite Hessian, you can find in that SD output, SD, PE, Hess, is just saying, it's a logical saying whether that Hessian is positive definite, and what you want it to be, and here it's saying that it is. So based on the two criteria we talked about, this model's converged. We can then extract stuff from the report and we can plot it. And if we look at the plot, here's the observed is shown in red, and the blue is the histogram that's predicted from the model. It's a little hard to see, so maybe I'll change that. Some breaks. Well, it's 20. So anyway, so the red is getting harder and harder to see, but we can see that the blue, the predicted distribution, is matching the red approximately. I'm not sure if this will work. Okay, log this. Okay, so the point of this was just to try to convince you that this fit is fitting okay. Okay, does anybody want to? How about we break into groups and people try making some change to this function. So how large of groups would people want to work in? How about we do like 4, 3, and 3? Does that work? And does anybody want help coming up with stuff that you could do to modify the code? You could switch the log normal to a normal distribution or a gamma distribution. You could try putting in additional covariates in the B_J and the Xij. Is that enough to go on for now? Okay, so yeah, so break into groups and I guess be prepared for somebody to report back to the group what you did in 10 minutes.
Hey, listen, do you have any ideas for?
Oh yeah, that's silly. Oh, how about, can one of you guys move over here? I forgot, I'm sorry, Jay, I was like just visually scanning. We should.
Yeah.
And if you want help, Jay and I obviously are here now.
That's a good question. Wait, that's good. Do you have any ideas of what features we want to add?
Just kind of what we've done in, just like a negative binomial.
Sure.
Wonder how that would work.
We have a bunch of built-in like parsed off probability distributions, so I wonder if we can just get one of those for negative binomial.
Yeah. Rather than code it themselves.
Yeah, that would be ideal.
It's in the, github.io.
Oh, nice.
Well, you still have to like merge.
Just found. Oh, yeah, okay, there's a dn binom function.
Oh, sweet.
That seems pretty appropriate.
Hey, how's it going? Good. So people online, I'm not sure how many people online are actually sitting with other people from the same city,
So,
which would of course make this more interesting. And I'm gonna pause the recording for now. Recording. And, does anybody remember how to get the Dockstrom documentation very easily? I think it's
.io website.
Here, I'll just go to this. I'm just scanning through the, let's see, TMB. So what's the website called?
Casker.github.io.
Okay, and then and then what do you do?
Then /adcomp /modules.html.
I should probably add this to the.
Is this what you want?
Yeah, exactly. So this is the this is like Dockstrom documentation. This is documentation for every function that's on the C++ side. And so if you go here and look up dtweedy, you see that there is a function called dtweedy that has inputs y, mu, phi, and p, and this int give log. And then basically very little documentation here. But at least it gives you a hint that it's using the same parameterization that John was talking about, where you've got mu, which is the expected count of individuals, phi and p. Well, actually, mu might be expectation of the distribution. There's a bunch of different parameterizations of Tweedy, and I always get mixed up about which one they're using. Anyway, so that's cool. I'd be curious to hear about it. And what did you guys look at again?
We were doing moving it to Poisson distribution. And so all we had to do was on line 36. Well, we had to actually, or
We got rid of SD.
yeah, had to subset out at log SD on 25 and 41, and then put D Poisson or D plus in on line 36.
And did you get it running, or?
Yeah, it works, but you have to exponentiate the linear predictor, otherwise it bombs.
And so I would have thought that would not give you the standard errors. Did you get that far, or?
It reported standard errors for when I exponentiated it.
Okay. And so maybe you passed it theta. I guess my hypothesis was that theta z would, because you're removing the use of, I guess, the second element of that, you'd have to make sure you pass theta z just as a scalar, not as a vector of length 2. Is that correct that you did that on the R side?
I passed it both, but then it returned just the second theta 0 was just 0.
Okay.
So it's never changed, I guess.
But yeah, I would have thought that, well, anyway, I would have thought that when you calculate the standard deviation, because there's no gradient to that one, the Hessian would be positive semi-definite and not invertible. And so if you do the SD report function, I'm surprised that it would have worked, but we can come back to that later. And also, I'm not exactly sure what it would be doing, because the dpros is expecting a whole number response. And so maybe I would have expected that you'd have to round it. Or
No,
something.
sorry, it didn't converge. So
Okay.
it did not converge.
Okay, yeah. So it probably didn't converge because of that third parameter, but also the dpros, I'm not sure what it's doing internally. Maybe it's rounding the data to fit a discrete distribution. It's actually kind of funny that I mean, ideally it probably should have given like an error message or something. Let's see, I'm not sure on the R side what happens if you try to get dpros for x equal 1.1. Yeah, so it gives a warning, non-integer x equals 1.1 on the R side, because a Poisson distribution is expecting all of the data to be whole numbers.
What if you put in x equals 1, lambda equals 1.1?
So that's fine, because lambda, the data is x, and lambda is the linear predictor. That could be any, positive real number. Anyway, but it's interesting. You could definitely do it that way. I just expected we're gonna figure out that you had to like round the data or something so that it was whole numbers.
Yeah, even when I take out the second, that second theta z, it still doesn't converge. Like it has a Hessian matrix, but doesn't. Yeah.
Yeah.
So.
Well, we can come back to that later. Yeah. Okay, so maybe I'll shift gears and look at the homework a little bit, and then we can look at the final. Well, the final material I wanted to get through was sort of how to evaluate fit. So we talked about convergence, we talked about optimization. Here is, it's always smart to plot the predictions versus the observations. So in this case, if you plot them, it looks like you maybe get kind of a decent looking match of the observed versus the predicted. That Delft model. There's a few different ways to assess fit. So what do people typically use? I mean, like in ecology, there's sort of ways that we do model selection. So what do we typically use for model selection?
AIC or MSE?
Yeah, AIC is sort of, I think since Burnham and Anderson, ecologists all just get used to doing AIC. And I don't really want to, I won't get into sort of when it makes sense and when it doesn't, but that's our kind of common practice in ecology at least. And we also sometimes do simulation experiments where you look at mean squared error, MSE. Has anybody used posterior predictive loss, or is that something people are used to talking about? John, you know your head. The kind of beard scratch could be a yes or a no.
Yeah, I'm trying to remember.
Yeah, so if anybody's interested in sort of model selection, there's this good Gelman paper. There's also a Hooden and Hobbs paper, and there's it's a topic that people publish on frequently, model selection. But I think a lot of people are kind of converging on the claim that the best criteria for model selection is some form of predictive loss.
Is it recording now?
I think it's recording now, yeah. So I think I took this from Gelman, from this Gelman book, that predictive probability is, let's see. So you've got you got a true data generating process F. You specify a model with some parameters and define that as a likelihood. You maximize that likelihood with respect to the parameters, and that gives you a predicted probability of some new data. So you can calculate what's the probability of some new data, y prime. And the predicted probability is the product of this predicted probability times the probability in the true data generating process integrating across the new data. And of course, this requires F, which you don't actually have. We don't directly observe the data generating process. But it's still useful to think about because it's sort of a proxy for what the data would be if we went out and replicated the experiment. And so instead, what we can do is do cross-validation, where we leave out some data, we fit the model, and then we calculate the probability of the held-out data under the model, and calculate the loss. What's the probability of those held-out data under the predictions of the model, and use that cross-validation loss as a measure of fit. So one way to do that is this k-fold cross-validation, where you divide your data set into k even partitions. You loop through all of those partitions where if you do 10-fold cross-validation, you divide it into 10 even partitions. You fit the model to partition 2 through 10, predict the data in partition 1, and then calculate the probability of the data in that unfitted partition 1, given the parameter estimates from the other data, and repeat that for all 10 partitions, and then calculate what's the average predictive probability of left out data in that process. So we can do this for every data point individually, and that would be sort of the best way. Leave one out. Cross-validation is sort of the best measure of collecting one new data under the same process. But of course, that involves fitting the model over and over again. So people do this like 10-fold or 5-fold cross-validation a lot. So any questions about that? We'll use this for the homework as well.
Is there any good rule of thumb for like what your space of models should be? Like, so if this is the way that you test a single model, like what should you be varying across different models to see?
Yeah, I don't think there is any good rule of thumb. There's in ecology, there's a little growing literature about fitting sort of machine learning or completely non-parametric models, using that as a metric of how much you could explain theoretically, and then trying to develop sort of a structural model that's based on biological intuition and see what proportion of that machine learning model you can explain with a mechanistic or structural model that you interpret. So, I think that's one answer. Barnum and Anderson say that you should never fit a model that doesn't have some theoretical support. Otherwise, you're kind of data dredging. So that's cross-validation. And then finally, people, I don't know how many people are used to confidence intervals and confidence interval coverage, but we'll want to confirm. So, we talked about the asymptotic normality. We didn't really talk too much about it, but John brought it up that we can calculate the standard errors of our parameter estimates from the shape of the likelihood function. So we take the second derivatives, that's the matrix called the Hessian matrix, and we can invert that and look at the diagonals of that, and that's an estimate of the variance for each parameter. And somebody, maybe it was Nat, brought up that, why do people just look at the diagonals as standard error instead of the whole matrix? And that's just kind of common practice, that it doesn't have any necessarily good theoretical justification. But anyway, so the point is that the shape of the likelihood function is an estimator for the standard errors. And so under a well-behaved model, we know that it'll be normally distributed around the true value. And also, I didn't talk about it, but we said that standard error estimate will be a good estimator for that, how far we are from the true value. And so under a correctly specified model, we should get what's called nominal coverage, where if we fit the model, we estimate the standard error, the confidence intervals should contain the true value at the kind of declared proportion of times. So if we calculate a 50% confidence interval using this formula based on the standard errors, if we do that when we correctly specify the model and we replicate that 100 times, it should contain the true value 50 of those times on average. And what would be the distribution of that coverage based on what we've talked about? So if we replicate that experiment with 100 replicates, we know it should be 50, but how much variance would we expect in that experiment?
Is that a binomial distribution?
It's a binomial distribution. So yeah, you could work out what's the confidence interval on that replicated experiment of confidence interval coverage using a binomial. And that works because each simulation replicate, the way we're defining it, would be independent of every other one. Okay, so that's sort of the, this is the definition of a confidence interval based on the standard errors. And this is sort of a verbal description of what I just said. So the homework is posted, and the homework is to basically to demonstrate that you can use template model builder, that you can modify the code, and that you can run a replicated simulation experiment and interpret sort of correctly specified or misspecified models. So that's sort of the net, I think those are the main points from this first week. All of the, these 4 homeworks, each person's expected to do it. Everybody's expected to program it themselves. You can work in groups, but you can't copy paste. It's an expectation that you can copy paste the code that I've sent you. But if you work in groups, each of you has to type the changes that you make to that file yourself. And that process of typing, I think, is sort of important for people to remember and learn how to do coding. So that's, I think, covered in the plagiarism section of the course description. And people are expected to submit, basically a short description. I mean, I said 3 pages and I meant double spaced. And you could make it as short as you want to show, I really am, this again is for your own benefit. So you're expected to submit a description and then an R script and a single TMB file that can do all of this stuff. And so the exercise is to do what's called a 3x3 factorial experiment, where you've got 3 operating models, you've got 3 different models that you use to simulate data, and then you've got the same 3 models that you fit each replicate. And each of those combinations of 3 estimation models and 3 operating models you replicate 100 times. And the 3 models, one of them is a generalized, this delta log normal distribution, one of them is a delta log normal with an intercept. One of them is a delta gamma, and one of them is a model of your choice that could be a covariate, or it could be a Tweedy, or it could be whatever you want. So for each of those 3 models, you fit it in TMB to data for Pollock. You extract the parameter estimates. You then simulate data from that fitted model, and then you refit the simulated data with each of those 3 same models again. And you do that 100 times. So in that, you end up with a table, a 3x3 table, saying something about, I forget exactly what I said. For each model, the average log likelihood of the data, the number, so you have to summarize for the fitted models, the likelihood of the data, the number of parameters, and the posterior predicted score from a 10-fold cross-validation experiment. You can show code for that in a second. And then there's this replicated simulation experiment that I just described. So does that make sense? Are all those concepts clear from what we've talked about? If yes, we can look at how to do the cross-validation experiment using the code. Any questions? So the final piece of code today was a new model called Delta Model version 2 that I compile, or I recompile it, and then on the R side, this function sample 1 through k size length CPUE replace equals true means that every datum is being assigned an integer from 1 to 10. So for 7,608 data, each one of them gets a number from 1 to 10, and then for the first cross-validation loop, I pass it the same stuff that we were doing before, except I've got this new input, pred TFI. So pred TFI, which stands for, pred TFI is saying if it was of partition 1, then do a 1, otherwise a 0, where 1 means true and 0 means false. And it's basically just saying that this data pred TFI, 10% of them are 1s and 90% of them are 0s. And so in the code that is otherwise identical, there's now this data vector pred TFI. It loops through and calculates the joint negative log likelihood for each data. And if pred TFI equals 0, which means it's not a predictive part, it assigns it to joint negative log likelihood. Otherwise, it assigns it to this object called pred JNLL. And then at the bottom, it's fitting just to the JNLL. So it's only fitting to the data where pred TFI equals 0. And if pred TFI equals 1, it reports that out, but it's not fitting to those data. So this is just an easy way to code up a predictive experiment where it's fitting to 90% of the data, and 10% of the data it's not fitting to, but it's still calculating the likelihood of those data and reporting it back out. So if we fit this model, the one other new piece here is that I'm using this TMB helper optimize function with Newton steps equals 1. And that's just taking a Nelder V optimizer and doing a little bit of extra stuff on top of it to get the final gradient to be better. So if we look at the opt, it now has this diagnostics built in. It has the AIC built in. It tells you a little bit about the convergence. It's just a function that I built to try to make optimization a little more friendly. And the final gradient we can see is down at like 1 billionth, because after it does optimization, it's doing this Newton step to get really close to the, the 0 gradient. So anyway, so you can still do this check of convergence. So it didn't encounter any problem with the convergence, and then I extract the predictive negative log likelihood from the report. So there's something called pred JNLL, and that is returned because I defined it on the CPP side, and I said report pred JNLL there. So that pred JNLL is the predictive log likelihood. I record it in a vector, and I can just loop through this. And this is the predictive log likelihood for each of the partitions of the data. So this is the results of that cross-validation experiment. And then finally, this is my really terse way of saying the average log likelihood per data on average across the 10 simulation experiments is 1.59. So the punchline of the simulation experiment will likely be that you will have best predictive log likelihood. This number will be highest when you are fitting a model with an estimation model that matches the model you're simulating data from. And that's sort of the point that I want to confirm to you using this experiment. So in your replicated experiment, you will do this. You'll put a loop around this for 100 loops of the simulation, and you'll also loop through the 3 fitting models and the 3 estimation models. And you'll have to record the predictive log likelihood for each of those replicates for each estimation model and each simulation model. So we have half an hour left. I'd be happy to just have, people are welcome to sit and start working on the homework if you want, and Jay and I can go around. Or we can discuss stuff. Any lingering questions?
I still have some questions about the optimization part.
Yeah.
So before we were doing, I think, NLM and B for our first lecture one, but then would you recommend just to start off for like easy, likely to converge optimizer to use your TMB helper optimize?
Yeah, and so you can always look at what the R code is by typing a function. And so TMB helper optimize is a big block of code that looks like this. But if you scroll up, it's kind of hard to read the way they end up formatting it. The main big part of the function is doing this NLMB, So TMB helper optimize is actually running the NLMB, and then it's redoing the NLMB several times based on the starting value from the last time, which gets it a little bit better. And then it does what's called a Newton step over and over again, which is how it gets the likelihood really low. And then it puts in some additional stuff that the NLMB doesn't give you in terms of outputs. And then if you tell it to, it does, if get SD equals true, it runs the SD report, but with some other stuff bundled into it that I'm not going to talk about. So the point is, it's essentially doing the NLMB, it's documenting the output better, it's building in some other stuff to make sure the conversions will be tighter, and it's accessing the SD report in a kind of more detailed way. So yeah, I mean, if I were you, I would just stick with the TMB helper optimize.
Yeah, seems great.
Any other questions or? So I'll probably stop the recording, and people are welcome to stay or leave, and if I think Jay and I will just sit here until 11:30 and try to go around if people have questions. Okay, thanks everyone.